Welcome to Sleepy Crimes. I am Anna, your host. Tonight, we drift into the shadows of the very ground beneath our feet, exploring the grand, slow-motion mystery of plate tectonics. Before we begin our journey through time and stone, I want you to find a place of absolute comfort. Settle into the softness of your blankets. Feel the weight of your body pressing gently into the mattress, supported and safe. Imagine the air around you is cool and still, like the atmosphere of an ancient library at midnight. The world outside is hushed, and the only thing that matters is the steady rhythm of your breathing. In and out, in and out. Tonight, we are going back to a time when the world was being redefined, one map at a time. We are heading to the late 16th century, to a small, candle-lit room in Antwerp, where the first whispers of a broken world began to surface. Imagine the year is 1596. The air is thick with the scent of beeswax and old vellum. Outside the window, the cobblestone streets of the Spanish Netherlands are damp with evening mist, but inside, the workshop of Abraham Ortelius is a sanctuary of quiet discovery. Ortelius was a man of precise vision, a master cartographer who spent his days painstakingly rendering the outlines of our planet. Picture him sitting at a heavy oak desk, his fingers stained with the dark indigo and sepia inks used to bring continents to life on paper. The light from a single tallow candle flickers, casting long, dancing shadows across his latest work, the third edition of his great geographical dictionary, the Thesaurus Geographicus. There is a soft, rhythmic scratching sound as his quill moves across the page, capturing the names of distant ports and vast, uncharted oceans. But tonight, his mind is not on the details of the cities, but on the shapes of the land itself. As he looks down at his maps, Ortelius notices something peculiar, something that many had overlooked in their haste to colonize and trade. He traces the eastern coastline of South America with a steady hand, following the sweeping curve of Brazil as it reaches out into the Atlantic. Then he shifts his gaze across the blue expanse to the western coast of Africa. He pauses. The candlelight catches the curvature of the paper, and in his mind, he begins to slide the continents toward one another. The sharp, inward tuck of the African coast near the Gulf of Guinea seems to mirror, with haunting precision, the outward bulge of the South American continent. It is as if he is looking at two pieces of a grand, celestial jigsaw puzzle that have been pulled apart by a giant, invisible hand. The fit is too perfect to be a mere coincidence. He feels a quiet chill, a realization that the world he is mapping might not be as static as everyone believes. In the silence of his study, Ortelius begins to formulate a radical thought. He writes that the Americas were torn away from Europe and Africa by earthquakes and floods. He mentions the ancient legends of Atlantis, or Gadricus, as Plato called it, suggesting that a massive rupture had occurred in the deep past. To Ortelius, the evidence was written in the very edges of the earth. He notes that the vestiges of the rupture reveal themselves to anyone who brings forward a map of the world and considers carefully the coasts of these three continents. He imagines a time, thousands of years before his own birth in 1527, when a traveler could have walked from the plains of Africa into the forests of South America without ever crossing an ocean. It is a lonely thought, sitting there in the 16th century, to imagine the earth beneath his boots as something that can break and drift. The maps Ortelius created were part of the first modern atlas, the Theatrum Orbis Terrarum, or the theater of the world. Each page was a masterpiece of engraving, decorated with sea monsters and ornate compass roses, yet hidden within those artistic flourishes was a scientific truth that would wait for over 300 years to be fully understood. He did not have the tools of modern geology, nor did he know of the molten currents deep within the mantle. He only had his eyes, his maps, and the quiet intuition of a man who looked at the world as a single, connected entity. As you lie there, imagine the slow, tectonic pulse he was just beginning to sense. The continents are not islands of stability, but great vessels of stone, drifting on a hidden sea of heat. They move so slowly that a human life is but a blink in their journey. Yet they are always in motion, following the ancient lines of the rupture that Ortelius first saw in the flickering light of his Antwerp home. His observations in 1596 were like seeds planted in the frozen ground of scientific history. They would lay dormant through the centuries, through the age of sail and the Industrial Revolution, waiting for others to look at the same coastlines with fresh eyes. But the primary credit belongs to that quiet cartographer who dared to wonder why the world looked like it had been broken. As we conclude this first chapter of our journey, let your thoughts drift like those ancient landmasses. Feel the vastness of time and the slow, deliberate pace of the Earth's transformation. You are part of this grand design, resting safely on a world that is always evolving, always shifting, yet providing a steady foundation for your rest. Breathe deeply now, as we prepare to move from the maps of the past into the deeper secrets of the Earth's core. The journey is just beginning, and the silence of the night is yours to keep. The air in Frankfurt on that evening of January 6, 1912, was crisp with the biting edge of midwinter. Inside the Senckenberg Museum, the gaslights flickered against the polished wood and the towering, dusty skeletons of long-dead giants. Alfred Wegener, a man whose eyes held the clarity of the high-altitude air he so often studied, stood before the German Geological Society. He was a meteorologist, a self-described outsider in this gathering of stone-hardened geologists who believed the Earth's features were fixed in place forever. Imagine the silence in that room. It was heavy, expectant, yet layered with a subtle, simmering doubt that felt almost electric. He carried with him a leather portfolio filled with a vision of a world that was not anchored, but fluid, a world that breathed and shifted over eons. To those gathered, the mountains were eternal monuments, yet Wegener was about to tell them that the very ground beneath their heavy boots was a tireless traveler. His voice was steady, cutting through the hushed murmurs as he spoke of a single, ancient landmass, a supercontinent he would later name Pangaea. He described the Earth's crust not as a solid, unchanging shell, but as a series of great granite ships drifting slowly through a sea of denser basalt. He used the term continental drift, or continental Verschiebung. The words felt radical, almost poetic, yet they were backed by a meticulous collection of data that had consumed his thoughts for years. He spoke of the jigsaw fit of the coastlines, showing how the great bulge of Brazil seemed to seek the hollow of Africa like a lost piece of a child's puzzle. He demonstrated how the Appalachian Mountains of North America were brothers to the peaks in Scotland and Norway, separated now by the vast, dark Atlantic, but identical in their mineral soul. The scholars shifted in their seats, the sound of their woolen coats rustling like dry leaves against the weight of his impossible, shifting truth. It was in the small, silent witnesses of the deep past that Wegener found his most haunting evidence. He spoke softly of the Glossopteris, a fern with tongue-shaped leaves that had once flourished in a world now divided by thousands of miles of salt water. How could the heavy seeds of a plant cross the crushing expanse of the ocean? They could not. He spoke of the Mesosaurus, a small, freshwater reptile whose delicate bones were found in both the red sands of South Africa and the sun-drenched earth of Brazil. This creature, built for the gentle currents of rivers, could never have survived a journey across the brine of the Atlantic. To Wegener, these fossils were not just curiosities. They were the torn pages of a book that had once been whole. He felt the texture of the evidence in his mind, the rough grain of the sandstone, the cool, smooth surface of the petrified leaves. It was a vision of a prehistoric garden, once unified under a single ancient sun. Shortly after shaking the foundations of the scientific world in Frankfurt, Wegener followed the siren call of the North once again. In mid-1912, he embarked on his second expedition to Greenland, a land of white silence and terrifying, majestic beauty. He was no longer just a theorist sitting in a library. He was an explorer seeking the pulse of the planet in its most frozen reaches. Arriving at Danmarkshaven, the air was a sharp, crystalline blue, smelling of salt and ancient, compacted snow. He traveled with a small, dedicated team, including the leader Johan Peter Koch. They brought with them hardy Icelandic ponies, their breath blooming like white clouds in the freezing air, and sled dogs whose low howls echoed against the crystalline walls of the glaciers. Their goal was to cross the vast, unknown interior ice sheet, a place where the wind sang a song of absolute, crushing desolation, and the horizon vanished into a blur of white. The expedition was nearly ended before it truly began, a reminder of the Earth's raw power. While they were attempting to climb a massive glacier on the northeast coast, the ice itself seemed to rebel against their intrusion. With a sound like 1,000 cannons firing at once, the glacier began to calve. Enormous blocks of ice, the size of great cathedrals, broke away and crashed into the churning sea, sending plumes of freezing spray and shards of ice into the air. Wegener and his companions escaped only by a miracle, the ground beneath them trembling as the landscape rearranged itself in a matter of heart-stopping seconds. Koch fell into a deep, hidden crevasse, his legs snapping with a sickening crack that was muffled by the heavy, falling snow. For months, they were forced to wait, the isolation pressing in on them like a physical weight, as Koch healed in a makeshift sickbed, while the Arctic winter descended in a shroud of endless, velvet night. They became the first men in recorded history to overwinter on the inland ice of Greenland, a feat of incredible endurance. Their small hut was a tiny, flickering speck of warmth in a desert of infinite white. Outside, the temperatures plummeted to 60 degrees below zero, and the wind hammered against the wooden walls with the force of a living thing. Inside, they lived by the soft light of oil lamps, the air thick with the smell of kerosene, dried meat, and damp wool. Wegener spent his long hours obsessively recording data, his pen scratching rhythmically across the paper as he noted the movements of the atmosphere and the immense thickness of the ice. They bored a hole 25 meters deep into the glacier, pulling up cores of ice that held the secrets of thousands of years of weather. To Wegener, the ice was a fluid entity, flowing just like the continents themselves, a slow-motion river of time that confirmed his belief in a dynamic, restless Earth. When Wegener finally emerged from the white wilderness in 1913, he carried with him volumes of unique data and a heart hardened by the northern frost. He had traversed 750 miles of barren snow and ice, rising to heights of 10,000 feet, all to understand the hidden mechanics of the world. He returned to a scientific community that was becoming increasingly hostile to his ideas, but he remained undeterred by their scorn. He saw the world as a grand, slow dance, where the continents waltzed across the globe over millions of years. In this chapter of his life, the Arctic vision was not just a scientific pursuit. It was a testament to the endurance of a man who looked at the frozen, unmoving horizon and saw a planet in constant, beautiful motion. The seeds he had planted in Frankfurt were now nourished by the deep ice of the north, waiting for the rest of the world to catch up to his quiet, revolutionary truth. Imagine the transition. From the howling, crystalline winds of the Greenland ice cap to the heavy, silent air of a German university lecture hall. It is 1915. Alfred Wegener has traded his rugged polar furs for a formal suit, but his mind is still traveling through deep time. He sits at a heavy oak desk, the air thick with the scent of dried ink and the faint, metallic tang of a ticking radiator. Before him lies the manuscript that will challenge the very foundation of the Earth. He calls it The Origin of Continents and Oceans. In these pages, he has gathered the clues we explored before, the matching fossils of the ancient Mesosaurus, the mountain ranges that end abruptly at the sea only to reappear on a distant shore. But as the ink dries, a different kind of cold begins to settle around him. It is not the bite of a polar blizzard, but the icy silence of a scientific community that is not ready to move. When the book is finally published, it spreads through the libraries of Europe like a slow-moving tide. In the quiet corners of study rooms, geologists turn the pages, tracing the maps with hesitant fingers. They see the supercontinent of Pangaea, a name Wegener chose meaning all lands, looking like a great, shattered heart that has been pulled apart. To Wegener, the evidence is overwhelming. He sees the Earth as a dynamic, living thing. But to his peers, the idea is more than just radical. It is physically offensive. They live in a world of fixity, where the continents are anchored deep into the heart of the planet. They look at his maps and then out their windows at the solid ground beneath their feet, and they feel a profound sense of disbelief. How could something so massive, so seemingly eternal as a continent, simply drift through the deep floor of the sea? The criticism begins as a murmur and grows into a roar. The most pointed questions are not about the what, but the how. The geologists of the early 20th century demand a mechanism, an engine that could possibly drive a landmass across the globe. Wegener, drawing on his experience as a polar explorer, offers an analogy. He suggests that the continents are like great icebreakers, plowing through the solid floor of the ocean. He imagines the lighter granitic rock of the continents sliding over the denser basaltic rock of the sea. But this is where he hits a wall of cold, hard physics. His colleagues point out a glaring flaw. The ocean floor is not like soft sea ice. It is rigid, brittle, and incredibly strong. For a continent to plow through it, the forces required would be astronomical. It would be like trying to push a heavy brick through a sheet of solid, unyielding steel. Into this fray steps a man whose name becomes synonymous with the opposition. Sir Harold Jeffreys. He is a brilliant geophysicist from Cambridge, a master of numbers and logic. In the mid-1920s, Jeffreys applies the cold blade of mathematics to Wegener's theory. He calculates the forces Wegener proposed, the centrifugal force from the Earth's rotation and the tidal pull of the sun and moon. Jeffreys' conclusion is devastating. These forces, he proves, are far too weak. They are as insignificant as a single grain of sand trying to move a mountain. He argues that if the tidal forces were actually strong enough to move a continent, they would be so powerful that they would stop the Earth from rotating entirely within a single year. The scientific world listens to the math. They trust the equations more than they trust the visual poetry of the coastlines. To them, the case is closed. Without a motor, the ship of continental drift is dead in the water. The climax of this intellectual rejection occurs across the ocean in 1926. A grand symposium is held in New York City by the American Association of Petroleum Geologists. Wegener is invited, a quiet man who stands out among the boisterous American scientists. He sits in the back of the room, puffing slowly on his pipe, his eyes steady as speaker after speaker takes the stage to dismantle his life's work. Some are polite, calling his theory a beautiful dream or the work of a poet. Others are far more biting. One prominent geologist asks, with a heavy layer of sarcasm, how we can call geology a science if we allow such footless theories to run wild. They mock his background as a meteorologist, suggesting he is an outsider playing a game where he does not know the rules. Through it all, Wegener remains silent, a man who knows that nature does not care for the opinions of men, but the weight of the dismissal is heavy nonetheless. By the end of the 1920s, Wegener's theory is largely relegated to the fringes of science, labeled as a curiosity or a fringe fantasy. He struggles to find a permanent professorship in Germany, eventually finding a home at the University of Graz in Austria. But his heart remains in the high, white silence of the north. In 1930, he returns to Greenland for one last expedition, seeking to measure the very movement he believes in. He disappears into a winter storm, and when his body is found months later, he is buried beneath the snow with his pipe by his side. He dies knowing he is right, but without the evidence of the motor that would prove it to the world. The theory of continental drift is buried with him, covered by the same ice he loved, waiting for a new generation to find the keys to the engine he could only dream of. The 1930s passed in a sort of academic silence, a decade where the revolutionary whispers of Alfred Wegener were buried beneath the weight of tradition. The scientific world had settled back into its comfortable, static chair, convinced that the Earth was a solid, unmoving monument to time. But as the 1940s dawned, the world was thrust into a conflict that would change everything, not just on the surface of our maps, but in our understanding of the very ground beneath our feet. The Second World War brought a desperate, driving need for innovation, and in the shadow of that chaos, the ocean began to give up its secrets. For centuries, we had looked at the sea as a vast, blue void, a flat expanse of water hiding a featureless wasteland of mud and silt. We imagined the abyss as a quiet, dusty basement of the world, where nothing changed and nothing moved. We were about to learn just how wrong we were. The key to this revelation was sound. In the deep, dark reaches of the Atlantic and Pacific, where light could never penetrate, the military needed a way to see. They developed sonar, an acronym for sound navigation and ranging, a technology born from the necessity of hunting silent steel predators beneath the waves. Imagine being on the deck of a heavy naval ship in 1942. The air is cold and carries the sharp, metallic tang of salt and diesel. Below the waterline, a transducer sends out a sharp, rhythmic pulse, a metallic ping that travels through the heavy pressure of the deep at over 5,000 feet per second. It is a lonely sound, a call into the dark that waits for an answer. When that sound hits something solid, it bounces back, returning as a faint, ghostly echo. By measuring the exact time it took for that echo to return, sailors could suddenly see the invisible. They were no longer sailing over a void. They were measuring the heartbeat of the Earth's hidden skin. Among those listening was a man named Harry Hess. Before the war, he was a geology professor at Princeton, a man with a quiet, analytical mind who was deeply curious about the planet's structure. When the war began, he became the commander of the United States ship Cape Johnson, an attack transport vessel. While most captains were focused solely on the immediate dangers of the horizon, Hess did something unusual. He left his ship's sonar, or echo sounder, running almost continuously, even when he wasn't in combat zones. As he crisscrossed the Pacific, moving toward landings at places like Iwo Jima and the Philippines, the machine on his bridge was constantly scratching lines onto long rolls of paper. Each line represented a depth, a measurement of how far the bottom was from the hull. Hour after hour, day after day, the pen moved, translating the invisible echoes into a physical record. Hess was essentially mapping the world, while the world was trying to tear itself apart. What Hess saw on those scrolls of paper was staggering. The ocean floor was not a flat bathtub of mud. It was a jagged, violent landscape that rivaled the highest peaks of the Alps or the Andes. The sonar revealed massive underwater mountains, some of which had peculiar, flat tops. Hess called these drowned volcanoes guyots, named after a geographer from the 19th century. These were not just random rocks, they were clues. He found vast canyons that made the Grand Canyon look like a mere crack in the pavement. Most importantly, the data began to show a massive, continuous ridge running down the center of the Atlantic, a spine of mountains that seemed to hold a secret rhythm. This was the first time humanity realized that 70% of our planet's surface was a complex, dramatic terrain of valleys and peaks, hidden in the perpetual night of the deep. The silence of the abyss was actually a chorus of geological history, waiting to be interpreted. The data from the war years didn't just stay in naval archives. It eventually flowed into the hands of visionaries like Marie Tharp and Bruce Heezen at the Lamont Geological Observatory. Marie, a woman of immense patience and skill, was initially barred from going to sea because of her gender. So, she sat at a drafting table in New York, surrounded by those endless rolls of sonar data. She took the raw, chaotic numbers and began to translate them into art. With pens, ink, and rulers, she painstakingly drew the texture of the ocean floor, degree by degree. She noticed something that others had missed, a distinct, deep valley running right down the center of the mid-ocean ridges. She called it a rift valley. When she first suggested that this rift indicated the continents were moving, her colleague Bruce dismissed it as girl talk. But the evidence was there, etched in the paper by the echoes of 1,000 sonar pings. The lines on the maps were beginning to form a picture of a planet that was very much alive. As the 1950s approached, the mountain of evidence became impossible to ignore. The echoes in the deep were telling a story of a seafloor that was not eternal and unchanging, but young and active. Harry Hess would eventually take his wartime observations and synthesize them into a bold new hypothesis. He began to think of the ocean floor as a conveyor belt, where new crust was being born at the ridges and destroyed in the deep trenches. The technology of war had inadvertently provided the tools for a peacetime revolution. Those rhythmic pings from the Cape Johnson had pierced the veil of the deep, and for the first time, we could see the skeleton of the world. The ghost of Wegener began to stir in the minds of scientists everywhere. The drift was no longer a fantasy of the fringe. It was becoming a measurable, undeniable reality. We were standing on the threshold of a new era, listening to the echoes of a moving Earth. In the quiet halls of the Lamont Geological Observatory, nestled in the woods of New York, a different kind of explorer was at work. While her male colleagues sailed across the churning waves of the Atlantic, Marie Tharp remained on land, confined by the rigid rules of the 1950s that forbade women from joining research vessels. But the distance from the salt spray did not limit her vision. In her office, the air was thick with the scent of aged parchment, India ink, and the faint smell of pencil shavings. The only sound was the rhythmic scratching of her pen against heavy paper and the occasional rustle of massive data rolls. These rolls were the voices of the deep, long strips of paper covered in jagged lines produced by echo sounders. Each peak and valley represented a pulse of sound. Marie's task was one of incredible patience. She took those millions of sonar pings and began to translate them into a landscape. It was like assembling a jigsaw puzzle where most of the pieces were missing. She would sit for hours under the warm glow of her desk lamp, plotting point after point, connecting the dots to reveal the texture of the abyss. Before this time, many scientists imagined the ocean floor as a featureless plain of mud, a silent graveyard where nothing ever changed. But as Marie worked, a different picture emerged. She wasn't just drawing a map, she was uncovering a hidden world. She saw jagged peaks that rivaled the Alps and canyons deeper than the Grand Canyon. The ocean floor was not a desert of silt, but a rugged, violent mountain range that stretched for thousands of miles. It was in 1952 that Marie noticed something peculiar while working on 6 transatlantic profiles. As she meticulously sketched the silhouette of the mid-Atlantic ridge, she saw a consistent, V-shaped notch carved directly into the crest of the mountains. It appeared again and again in her drawings, a deep, dark indentation that seemed to split the mountain range in two. To her trained eye, this was not a random coincidence or a mistake in the data. It looked like a rift valley, the kind of feature formed when the Earth's crust is being pulled apart by immense internal forces. She realized that if there was a continuous rift running down the center of the Atlantic, it would be the smoking gun for continental drift. It suggested that the seafloor was not static, but was actively tearing open. When she showed her discovery to her partner, Bruce Heason, the reaction was not what she had hoped for. The scientific community was deeply skeptical of continental drift, viewing it as a fringe theory. Heason, influenced by the prevailing winds of the time, famously dismissed her observation as girl talk. He believed the idea of a central rift valley was too close to Alfred Wegener's controversial ideas, and for nearly a year, he refused to believe the evidence right in front of him. Marie, however, was undeterred. She possessed a quiet, steely confidence born of her deep connection to the data. She continued her work, refining her sketches, and waited for the truth to become undeniable. She knew that the lines on her paper were not just ink. They were the heartbeat of a living, breathing planet. The confirmation finally came from an unexpected source. Another researcher in the lab, Howard Foster, was busy plotting the locations of earthquake epicenters across the globe. When Marie and Bruce compared his map of seismic activity to her topographic map of the ocean floor, the results were staggering. The epicenters of the undersea earthquakes fell into a nearly perfect line that ran directly through the center of Marie's Rift Valley. The shaking of the earth was happening exactly where she had predicted the crust was splitting. The silence of the deep was finally broken by the roar of the data. It was impossible to ignore any longer. The rift was real, and it was active. This alignment of mountain, valley, and earthquake was the bridge that connected the mystery of the seafloor to the grand movement of the continents. By the middle of the decade, the skepticism began to dissolve like salt in water. The discovery of the Mid-Atlantic Rift Valley, stretching for 10,000 miles, became a foundational pillar of what we now call plate tectonics. Marie Tharp had seen what everyone else had missed, not by sailing the seas, but by listening to the echoes they brought back to her. Her pens had traced the very seams of the world, revealing that the Earth is a puzzle in constant motion. As the 1950s drew to a close, the scientific world stood on the threshold of a revolution, finally understanding that the ground beneath our feet is a restless, shifting mosaic. The rift in the silence had become a loud, clear call to look deeper into the shadows of our planet's past, into the heart. As the discovery of the Mid-Atlantic Rift Valley began to settle into the collective consciousness of the scientific world, a former Navy commander turned professor named Harry Hess was looking at the data with a different kind of intensity. He remembered the 1945, when the air on the deck of the United States ship Cape Johnson was thick with salt and the world was at war. For Hess, that conflict had been the backdrop for a secret obsession. Between the frantic maneuvers of troop transport, there was a steady, rhythmic pulse coming from the hull of his ship. Ping, ping, ping. The echo sounder was a new tool designed to find the enemy, yet Hess used it to find the Earth. He kept it running day and night, tracing the unseen landscape miles below the keel. It was a dark world of jagged peaks and lightless plains that he now realized were connected to that massive rift. In those quiet wartime moments, Hess had studied the long scrolls of paper that the echo sounder produced. He had found something that should not have been there. Strange, solitary mountains with tops as flat as a tabletop, resting more than a mile beneath the surface of the sea. He called them guyots. These were not the jagged peaks of young volcanoes, but weathered remains. How could a mountain be planed flat by waves and then sink so deep into the abyss? It was a puzzle that stayed with him as the 1940s drifted into the 1950s. Back at Princeton, the data from the Cape Johnson did not gather dust. Hess realized that the ocean floor was not just a static basin, a dead container for the world's water. It was alive, moving with a slow, patient violence that defied everything geologists knew about the solid ground under our feet. By 1960, Hess had distilled these observations into a manuscript that would change the world. He titled it History of Ocean Basins, but in his introduction, he referred to his work as an essay in geopoetry. It was a beautiful term, a nod to the fact that his ideas were bold leaps of the imagination that technology could not yet fully prove. He sat in his office, surrounded by the smell of old paper, imagining the Earth not as a solid sphere, but as a dynamic machine. He looked at the maps of the Mid-Atlantic Ridge, that great, wounded rift running down the spine of the ocean, and he saw not just a mountain range, but a factory. Deep beneath the crust, the mantle was churning, driven by the intense heat of the planet's core. This heat created convection cells, massive circles of rising and falling rock that moved with agonizing slowness. Where the hot rock rose, it pressed against the thin skin of the ocean floor, splitting it open at the ridges. Here, in the darkness of the deep sea, the earth was literally birthing itself. Red-hot magma would ooze into the rift, meeting the freezing touch of the seawater and hardening into fresh, black basalt. This was the beginning of the conveyor belt. Each new pulse of magma pushed the older rock aside, a relentless, inch-by-inch expansion that forced the seafloor to grow outward from the center. It was a process of constant creation, a renewal of the foundation of the world. This was the missing piece that earlier scientists had lacked. The continents did not have to plow through the solid rock of the ocean floor. Instead, they were passengers. They sat atop the moving crust, carried along by the seafloor spreading beneath them as it traveled across the basins. Imagine a great, stony conveyor belt, emerging from the depths of the ridge and traveling thousands of miles through the silence. The ocean floor was not permanent. It was a transient skin, only a few 100 million years old. The earth was recycling its own surface, sweeping the old evidence away to make room for the new. At the trenches, the old, cold crust would begin its final descent, sinking back into the hot, pressurized embrace of the mantle. It was a journey into the interior, a return to the fire from which it had first emerged. This grand cycle, this geopoetry, ensured the planet remained young and active even as the stars aged above. In this rhythm, the story of our world was finally finding its pulse, moving toward a truth that was as beautiful as it was profound. Close your eyes and feel the slow drift. The air in the middle of the Indian Ocean is thick with salt, and the low, rhythmic hum of the research vessel, the HMS Owen. It is the early 1960s, and the surface of the water is a restless, deep indigo hiding secrets that have remained undisturbed for millions of years. Behind the ship, a long cable stretches out into the wake, disappearing beneath the foam. At the end of that line is a magnetometer, a sensitive instrument designed to feel the invisible pull of the Earth's magnetic field. As the ship moves, the magnetometer glides through the darkness of the deep, silently recording the whispers of the rock far below. There is a certain hypnotic quality to the steady pulse of the engines and the waves. Back in the ancient, stony halls of the University of Cambridge, two men were poring over these jagged lines with a focus that bordered on obsession. Drummond Matthews, an experienced geologist with a keen eye for detail, was supervising a young doctoral student named Fred Vine. Together, they were looking at something that many other scientists had simply dismissed as noise. The maps of the ocean floor were beginning to reveal a strange, striped pattern of magnetic readings. Dark bands where the magnetic pull was stronger, and light bands where it was weaker. To most, it looked like a chaotic mess, a zebra skin rug draped haphazardly over the underwater mountains. But for Vine and Matthews, there was a hidden logic buried in those stripes, a signature that suggested the Earth was restless. To understand what they saw, we must imagine the very moment a rock is born. Deep beneath the mid-ocean ridges, molten basalt rises from the mantle, glowing with a fierce, subterranean heat. This rock is rich in iron, and as it begins to cool, it reaches a critical threshold known as the Curie point. In that fleeting second, before the stone fully hardens, the tiny iron minerals within it act like microscopic compass needles. They align themselves perfectly with the Earth's magnetic field, pointing toward the North Pole. Once the rock solidifies, that orientation is locked in forever, a permanent record of the world's magnetic state at the moment of its birth. But here was the mystery. The Earth's magnetic field is not a constant thing. Every million years, the magnetic poles actually flip. Vine and Matthews realized that if the ocean floor was truly spreading, then the sea floor should act like a giant, slow-motion tape recorder. As the lava erupted at the central ridge and moved outward, it would record the magnetic field of the time. If the poles flipped while the floor was moving, the next batch of rock would record a reversed signal. This would create a series of parallel stripes, alternating between normal and reversed polarity. They focused their attention on the Carlsberg Ridge in the Indian Ocean, tracing the patterns with meticulous care. The stripes were not just random patches, they were continuous, stretching for hundreds of miles along the flanks of the underwater mountains. It was a binary code of the deep, a series of signals written in the language of magnetic forces. The true breakthrough came when they looked at the symmetry of it all. If you were to take a map of these magnetic stripes and fold it directly down the center of the mid-ocean ridge, the patterns on the left side would match the patterns on the right side almost perfectly. It was a mirror image. This symmetry was the smoking gun. It proved that the rock was being created at the center and then split in two, with each half moving away at exactly the same speed. It was as if the Earth was printing a twin-sided newspaper, sending the identical pages off in opposite directions. In 1963, they published their findings in the journal Nature, though the scientific community was slow to embrace such a radical idea. A similar discovery had been made by Lawrence Morley. Despite the initial skepticism, the evidence was undeniable. By the mid-1960s, more surveys from the Atlantic and the Pacific began to confirm the same symmetrical patterns. The stripes provided a way to measure the pulse of the planet, allowing scientists to calculate exactly how fast the oceans were growing. Some ridges were spreading at a rate of only 2 centimeters a year, while others were racing along at more than 15. This magnetic signature transformed the seafloor from a silent graveyard into a dynamic, living history book. The conveyor belt was no longer a metaphor. It was a physical reality, driven by the heat of the core and recorded in the very fabric of the crust. As the ink dried on their charts, the old, static view of the world crumbled away, replaced by a vision of a planet in constant, silent motion. The impossible truth. The ocean floors were speaking, but the grammar of their movement remained a cryptic puzzle. By the mid-1960s, the evidence gathered from the deep was overwhelming, yet it lacked a certain geometric elegance. We had seafloor spreading at the ridges and deep-sea trenches where the crust seemed to vanish, but the world is not a flat map. It is a sphere. As the rigid sections of the Earth's crust moved, they were forced to navigate a curved surface, and this created a mathematical nightmare for the scientists. If the seafloor was moving away from a central ridge in straight lines, why did the ridges themselves appear to be broken into staggered, zigzagging segments? The scientific community was missing the bridge that would connect these observations into a single, unified law of motion. Enter John Tuzo Wilson, a Canadian geophysicist who would eventually provide the missing piece of the puzzle. Wilson was a man of remarkable vitality, a bluff and genial professor who had spent his youth in the rugged Canadian wilderness. He was the son of a Scottish engineer and an adventurous mother who was a pioneering mountaineer. And perhaps it was this heritage of precision and exploration that allowed him to see what others could not. For a long time, Wilson had been a skeptic. Like many of his peers, he viewed the early ideas of continental drift as little more than a curiosity. But the 1960s were a time of transformation, and as the data grew undeniable, Wilson found himself reconsidering his stance on the world. He realized that the Earth was not a static rock, but a living, shifting machine. Wilson set his mind to understanding the strange geometry of the planet's movement. The problem lay in the way the great ridges were sliced. On the maps, these ridges were not continuous lines. They were offset by dozens of deep, horizontal gashes known as fracture zones. To the geologists of the era, these looked like simple tiers where the seafloor had been pulled apart. But Wilson sensed something more profound. He began to think of the Earth's surface as a series of rigid plates, a term he was the first to coin, which had to follow the laws of spherical geometry. He imagined the crust as a cracked porcelain shell, where each piece was forced to slide against its neighbor. This was the birth of the transform fault, a concept that would change everything. The breakthrough came in 1965 during a sabbatical at the University of Cambridge. In a moment that has since become legendary, Wilson was experimenting not with complex computers, but with a pair of scissors and a simple piece of paper. He cut and folded the paper to represent the ridges, sliding the segments back and forth to see how they interacted. Suddenly, it clicked. He had discovered a new class of fault that allowed the plates to slide past one another horizontally without creating or destroying a single inch of the surface. Wilson was so excited that he drew a diagram with a crayon and kept it in his wallet, ready to show the concept to anyone he met. He proved that the simplest tools could sometimes solve the most complex mysteries of our world. In his landmark paper, published in Nature in July of 1965, he explained that these transform faults were the essential connectors of the global system. They were the joints that linked the spreading ridges to the subduction trenches. Imagine two giant slabs of rock, miles thick, grinding against each other as they move in opposite directions. There is no volcanic fire here, no deep abyss where the land is consumed. Instead, there is only the immense, silent pressure of the slide, a conservative boundary that preserved the planet's size. This insight was the final geometric proof that the theory of plate tectonics was a mathematically sound description of a planet in motion. While most of these faults were hidden beneath the dark, cold waters, Wilson pointed to places where they reached the surface. The most famous is the San Andreas Fault in California. Here, the North American plate and the Pacific plate meet in a horizontal dance that has shaped the landscape for millions of years. When you stand on the edge of that fault, you are standing on the boundary of two worlds, watching the slow-motion collision of a continent and an ocean that has defined the very West. Wilson's faults turned the fractured map of the world into a coherent jigsaw puzzle. The skepticism that had greeted him when he first announced his discovery quickly evaporated as his colleagues realized he had unlocked the secret of the Earth's movement. The theory was now whole. We no longer saw a world of drifting continents, but a world of interlocking plates, each one a piece of a global machine. The Earth was finally understood as a collection of plates drifting in a grand, unified design, sliding and shifting in a silence that spans eons. Each plate, from the massive Pacific to the smaller Cocos, moves with an inexorable purpose, driven by the heat of the core. The stage was now set for the final realization of how these great plates drive the very life and death of our planet. The geometry was no longer a mystery. The faults of Tuzo-Wilson had smoothed the path. As we look across the vast expanses of our globe, we see a world that is not broken, but perfectly fitted, a puzzle of stone and sea constantly being remade. In the quiet of the night, the ground beneath you continues its ancient, measured slide, guided by the elegant laws of the sphere. The air of the late 1960s was thick with the scent of old paper and the quiet electricity of change. In laboratories from Princeton to Cambridge, the scattered fragments of a century-old mystery were beginning to hum with a shared frequency. For decades, the Earth had been viewed as a collection of isolated events, a sudden quake in Japan, or a strange magnetic stripe on the Atlantic floor. These were the whispers of a planet that no one quite knew how to listen to. But as the decade drew toward its close, the scientific world held its breath. The pieces were no longer just clues, they were becoming a map. We find ourselves in 1967, a year when the disparate threads of geology and geophysics finally began to weave into a single, shimmering tapestry of motion. In the cooling shadows of the Scripps Institution, a young researcher named Dan Mackenzie was looking at the world through the lens of pure geometry. Alongside Robert Parker, he began to treat the surface of the Earth not as a soft skin, but as a series of rigid pavements. They realized that if these slabs were truly rigid, their movements across the curved surface of a sphere must follow the strict laws of mathematics. They invoked the ghost of Leonhard Euler, the great 18th-century mathematician, applying his theorem of rotation to the very ground beneath our feet. This was the breakthrough. The movement of the Pacific floor was not a random drift, but a precise rotation around a fixed pole. Imagine a giant, invisible hinge anchored deep within the earth, around which 1,000 miles of rock slowly pivots. At the same time, through the quiet corridors of Princeton University, Jason Morgan was reaching a nearly identical conclusion. In the spring of 1967, he stood before his peers and presented a vision of the Earth that was startling in its simplicity. He proposed that the entire lithosphere was fractured into a series of massive, rigid blocks. These were the tectonic plates. Morgan's vision was one of a global equilibrium, a unified field where every movement in the Atlantic was echoed by a disappearance in the Pacific. He saw the transform faults, those deep, jagged scars in the ocean floor, not as accidents, but as the tracks along which these great plates slid. He understood that these plates were roughly 100 kilometers thick, riding upon a warmer layer that allowed them to glide with a silence that belies their unimaginable weight. By 1968, the French geophysicist Xavier Lepichon took these geometric concepts and fed them into the humming mainframes of the era. The computers of the late 1960s were massive machines of spinning reels and glowing tubes, yet they possessed enough clarity to calculate the first truly global model of our moving world. Lepichon's work was the final seal on the theory. He proved through rigorous analysis that the Earth's surface was an integrated system. For every inch of new crust that bubbled up from the fiery ridges of the mid-ocean, an equal amount was being swallowed back into the dark, crushing depths of the subduction zones. It was a perfect balance, a cosmic bookkeeping of rock and fire. His model initially identified 6 major blocks, but the framework was already expanding to include the complex 12 plates. We can visualize these 12 plates now, drifting through the dark currents of time. There is the vast Pacific Plate, a silent giant of basaltic floor, the North American and South American plates, carrying the weight of entire civilizations on their backs. The African, Eurasian, and Antarctic plates, cooling in their ancient positions. Then come the others, the smaller but equally vital actors in this drama. The Indo-Australian plate, the Nazca, the Cocos, the Philippine, the Arabian, and the Caribbean plates. Each one is a continent-sized island of rock, separated by boundaries that breathe fire or shudder with the tension of 1,000 years. Some plates are vast and heavy, like the floor of an ocean, while others are light and thick, crested with the granite of mountain ranges. Together, they form the 12 pieces of the unified field, a complete shell. The formalization of plate tectonics changed everything. It was the moment geology grew from a descriptive art into a predictive science. It explained why the Himalayas reached for the heavens and why the San Andreas Fault trembled in the golden light of California. All the disparate pieces, the magnetism, the earthquakes, the fossils, and the trenches, finally clicked into place. We now live with the knowledge that the ground is not a solid foundation, but a floating fleet of stone. As you lie there, feel the stillness of your room, yet remember the quiet, relentless journey of the plate beneath you. It moves no faster than a fingernail grows, yet it moves with a force that can lift oceans and crush mountains. The world is a unified field of motion, a slow and rhythmic pulse that has continued for billions of years. Previously, we spoke of how the formalization of plate tectonics changed everything. It was the moment geology grew from a descriptive art into a predictive science. It explained the ghost of the past, but tonight, we look at the physical, violent evidence of this theory. We look at the pulse of the planet. Imagine, for a moment, that the earth beneath your feet is not a solid, immovable mass, but a living, breathing machine of stone. This movement is so slow that our human lives are but a blink in its eyes, yet it is so powerful that it carves the very horizon. We begin our journey at the edge of the great oceans, where the world decides to recycle itself. These are the subduction zones, the silent, dark doorways where the heavy crust of the sea floor begins its long, final descent into the hot interior of the Earth. Picture the Mariana Trench, a vast, blue-black canyon cutting through the floor of the western Pacific. It descends more than 11,000 meters into the darkness. At these depths, the pressure is a weight beyond comprehension, yet it is here that the oceanic plate bows its head and dives beneath its neighbor. This is the first beat of the planet's pulse. As the oceanic plate slides downward, it does not go quietly. It is a world of grinding friction and immense heat. Think of two giant slabs of granite being pressed together with the weight of an entire ocean, then slowly, agonizingly, pulled across one another. This process happens at a rate of only a few centimeters every year, roughly the same speed at which your fingernails grow. But over millions of years, this steady movement builds a reservoir of energy that eventually snaps. We see this tension released in the great earthquakes that ripple through the deep crust. As the subducting plate sinks, it carries with it minerals and trapped seawater from the ocean floor. As it reaches a depth of about 100 kilometers, the heat becomes so intense that the plate begins to sweat. This water, squeezed out of the rock like a sponge, rises into the hot mantle above it. It acts like a catalyst, lowering the melting point of the surrounding stone and creating pockets of molten magma. This liquid fire is lighter than the solid rock around it, and so it begins a slow, upward journey toward the surface, fueled by the very water that once sat at the bottom of the sea. The result of this subterranean alchemy is the Ring of Fire. It is a horseshoe-shaped string of more than 450 volcanoes that trace the edges of the Pacific Ocean. From the snow-capped peaks of the Andes in South America to the mist-shrouded islands of Japan and the rugged cascades of the Pacific Northwest, these mountains are the visible scars of the subduction process. Each eruption is a reminder that the Earth is constantly turning itself inside out. The stratovolcanoes born here are often beautiful and symmetrical, their slopes built from layers of ash and lava, yet they are born from the violent destruction of the sea floor far below. When we look at the glowing lava of a volcano like Mount St. Helens or the distant, smoking cone of Mount Fuji, we are witnessing the return of the ocean's crust to the world of light. It is a cycle of renewal that has persisted for billions of years. A slow-motion metabolism that keeps our world geologically alive, while other planets have long since grown cold and still. But subduction is only half of the story. Sometimes, the movement of the plates brings two massive continents toward one another. Unlike the heavy oceanic crust, continental crust is thick and buoyant, made of lighter rocks like granite. When two continents meet, neither is willing to sink. Instead, they engage in a slow-motion car crash of epic proportions. This is what we call orogeny, the process of mountain building. The most magnificent example of this is the Himalayan mountain range. 50 million years ago, the landmass of India was a giant island, drifting northward across a vast body of water called the Tethys Sea. It was moving at a remarkable speed of about 9 meters every century. As it approached the southern edge of the Eurasian continent, the Tethys Sea began to shrink, its floor subducting and disappearing. Finally, the two great landmasses collided. Because they were of similar density, they could not dive under one another. Instead, the crust began to buckle, fold, and thrust skyward, creating the jagged, soaring peaks that define the roof of the world today. If you were to stand at the base of Mount Everest today, you would be standing on limestone that was once part of that ancient sea floor. There are fossils of marine creatures at the very summit, over 8,000 meters above the level of the sea. This is the ultimate proof of the theory. The Earth took the bottom of the ocean and pushed it into the clouds. Even now, this collision has not ended. India continues to push into Asia at a rate of about 67 millimeters per year. This pressure causes the Himalayas to rise by about 5 millimeters every single year, though the relentless forces of wind and ice weather them down just as quickly. It is a dynamic balance, a constant struggle between the upward push of the tectonic plates and the downward pull of gravity. The crust beneath these mountains has thickened to nearly 75 kilometers, twice the average depth found elsewhere. It is as if the Earth is bunching up its skin, creating a thick, protective layer where the continents have welded themselves together. This constant motion is the heartbeat of our world. It regulates the temperature of our atmosphere, recycles the carbon that sustains life, and creates the varied landscapes that we call home. Every mountain, every valley, and every ocean trench is a chapter in a story that began 4 billion years ago. As you lie there, safe and warm, the earth beneath you is performing this grand work. Somewhere, miles below the surface, a plate is slipping into the mantle. Somewhere else, a mountain is growing just a fraction of a millimeter taller. These changes are inevitable and unstoppable, yet they happen with a patience that is deeply comforting. We are passengers on a magnificent, shifting vessel, moving across the ages in a slow, rhythmic dance. The violence of the Earth's past has settled into a steady, reliable pulse. Let the scale of this time wash over you. Let the realization that the world is always changing, always renewing, bring you a sense of peace. The rocks are moving, the mountains are breathing, and the planet is cradling you in its ancient, steady hands. The case rests now. Let the details fade. You are safe. Close your eyes, breathe deeply, and have a good night. Sleep well. Previously, we spoke of the constant motion that acts as the heartbeat of our world. It regulates the temperature of our atmosphere, recycles the carbon that sustains life, and creates the very landscapes we call home. Tonight, we reach the final stage of our journey into the shadows of the eternal drift. We look back now at the middle of the 20th century, specifically the 1960s, a decade of profound change not just in our societies, but in our very understanding of the ground beneath our feet. For centuries, the map of the world was thought to be a static thing, a permanent stage upon which the drama of history was performed. But the scientific revolution of plate tectonics changed everything. It was a paradigm shift so vast that it has been compared to the discovery of the genetic code in biology or the birth of quantum mechanics in physics. It taught us that we are not standing on a solid, unmoving foundation, but on a collection of massive, restless vessels drifting across a sea of hot, pliable rock. The legacy of this discovery is not just found in textbooks. It is written in the very shape of the mountains and the depth of the trenches. Consider the vindication of those who came before. In 1912, Alfred Wegener was ridiculed for suggesting that the continents once fit together like pieces of a grand puzzle. He died in the frozen wastes of Greenland long before the world would admit he was right. We now see his vision in the symmetry of the seafloor, where magnetic stripes captured in cooling lava act as a recording of Earth's shifting magnetic poles over millions of years. Imagine the quiet intensity of the research vessels in the 1950s, their sonar pings cutting through the dark, cold waters of the Atlantic. It was here that Marie Tharp, a woman whose name was often left out of the earliest accounts, meticulously mapped the mid-Atlantic ridge. She discovered a rift valley so immense it could only mean one thing. The Earth was pulling itself apart and creating new skin in the process. This realization was the birth of the Great Global Rift Theory, the moment the static world died and the dynamic Earth was born. It is a legacy of bravery and persistence, of looking at a mountain range hidden under miles of ocean and daring to believe it held the secret to our planet's soul. This eternal drift is the great gardener of our world, shaping the very biology of life. When the supercontinent of Pangaea began to break apart roughly 175 million years ago, it did more than just move land. It created isolation. As the Atlantic Ocean widened at a rate of only a few centimeters every year, about the same speed as your fingernails grow, it separated lineages of plants and animals, forcing them to evolve in beautiful, unique ways. Think of the marsupials of Australia, drifting north on their own island continent, for tens of millions of years, or the strange and wonderful creatures of South America that developed in a world apart from the rest of the globe. Then consider the power of the collision. 3 million years ago, the drifting plates brought North and South America together at the Isthmus of Panama. This narrow bridge of land changed the currents of the oceans and allowed for the great American biotic interchange. It was a slow-motion meeting of worlds, where species that had never known one another finally crossed paths. This is the legacy of the drift, a planet that is constantly rearranging its residents, creating diversity through distance and unity through collision. Beyond the animals and the trees, plate tectonics is the silent architect of our climate. We live in what scientists call a Goldilocks climate, not too hot and not too cold, because of a massive geological recycling system. As tectonic plates are pushed deep into the Earth's mantle at subduction zones, they carry with them carbon-rich sediments from the ocean floor. This carbon is processed in the intense heat of the interior and eventually exhaled back into the atmosphere through volcanic eruptions. Without this conveyor belt, our atmosphere would lose its ability to trap heat, or it might trap far too much, leaving us as cold as Mars or as scorched as Venus. The very air you breathe tonight is part of a cycle that has been operating for billions of years. When the Great Himalayas rose 50 million years ago as India crashed into Eurasia, the fresh rock exposed to the sky began to soak up carbon dioxide from the air, cooling the entire planet and leading us toward the modern ice ages. Every breath we take is a gift from the grinding of the plates, a delicate balance maintained by the slow, heavy movements of the lithosphere deep beneath the soil. As we look to the deep future, we realize that the drift has no end. Scientists project that in another 250 million years, the continents will once again converge to form a new supercontinent, often called Pangaea Proxima. The Atlantic Ocean will close, the Americas will reunite with Africa and Europe, and the vast Pacific will grow even wider. It will be a world transformed, with new mountain ranges taller than the Everest of today and vast inland deserts where the ocean's moisture cannot reach. This cycle of assembly and breakup has happened at least 3 times in the past, and it will happen again and again until the Earth's core finally cools and the heartbeat of the plates falls silent. But that is billions of years away. For now, we are passengers on a restless vessel, moving through the cosmos on a journey that spans eons. There is a strange comfort in this scale of time. Our worries, our fleeting moments, are held within a story that began 4 billion years ago and continues with every silent inch the continents travel while we sleep. The story of the plates is a story of patience. It is the story of how heat becomes motion, how motion becomes land, and how land becomes the foundation for everything we have ever known. We are part of the Earth's long, slow exhaling. As you lie there, feel the stillness of your room, but remember the quiet power moving beneath you. The world is not finished. It is still being born, still drifting, still changing. The case rests now. Let the details fade. You are safe. Close your eyes, breathe deeply, and have a good night. Sleep well.